Good morning. I hope everyone is doing well today. The midterm grades were released this morning, so you should be able to see them. Can you see them on Gradescope? Yeah? Okay, great. Okay, good morning again. So yes, the midterm one grades have been released. I'll post the questions and the solutions on the website after class today. Okay? So let's continue. Today we want to discuss angular momentum and particle collisions. What did we do last time though? Does anyone remember? Yes. Exactly, power, work, and energy. And then at the end of lecture we introduce something else also. Yes. Exactly. Linear impulse, linear momentum. What is the linear impulse, linear momentum equation? The linear impulse, linear momentum equation. Exactly. It's just the integral of the balance of linear momentum with respect to time. So, linear impulse. The balance of linear momentum says that F is equal to G dot. The linear impulse momentum equation says that the integral of F dt So right now what I want to introduce next is the angular impulse, angular momentum equation. But before we do that, I want to review how we calculate the moment of a force from statics. Okay, so a force F is applied on a particle of mass m, and the position vector of the particle from the origin is what? Of the mass m, r, right? Okay, so what is the moment of F about O? What is the moment of the force F? F is being applied at the particle with mass m, having a position vector r from the origin. So what's the moment of F about O? Yes. R cross F. So is it that, or is it just the perpendicular distance from the origin to O crossed times F? Let me ask you this. Is the moment of a force, is it a scalar or a vector? It's a vector, right? So it should be a cross product. So it is actually the moment of the force F about O is equal to R cross F. The position vector, so I'm trying to calculate the moment of the force F about this point O. It's going to be the position vector from O to the force crossed with the force. which in magnitude is going to give you the perpendicular distance between O and the force times the force. Now, do you remember this? Any questions about this? What is the moment of F about P, about the point P? So again, I want to calculate the moment of this force F, but now about P instead of about the origin. What do I do? Cross product with what? R minus P. Fix it, you're missing something. Exactly. It's a position vector to P, right? So what is this equation saying? It's saying that if I want to calculate the moment of F about P, I'll take the position vector from P to F and I'll cross it with F. That's how we calculate the moment of a force. So we have to be very careful. The moment is a cross product. Its result is a vector. Can someone guess a common mistake students do when calculating the moment of a force? Yes, that's a very common mistake and it's very wrong. F cross R. They do F cross R instead of R cross F. This wouldn't give us the same answer, right? If I do F cross R, will I get the same answer as R cross F? No, I'll get an opposite. I'll get a minus sign. Okay? So this is how we calculate the moment of a force. Any questions? Okay. So now we're going to define the angular momentum. So consider the same particle M. Okay, so the angular momentum of a particle about O is, well, a better name for this instead of angular momentum is moment of linear momentum. What is the linear momentum of a particle M traveling with a velocity v? mv, right? The linear momentum of the particle is mv. And the moment of linear momentum is, instead of calculating the r cross mv moment of the force, calculate the moment of linear momentum, it's going to be r cross mv. And that's the angular momentum of the particle about O. So the angular momentum of the particle is defined to be r cross about O is r cross mv. In general, about any point P, it's going to be HP is equal to R minus RP cross MV. So that's the definition of the angular momentum of a particle about a certain point. So again, what's the linear momentum of a particle? It's mv. What's the angular momentum of a particle about any point P? It's R minus RP cross mv. And a better name for angular momentum is moment of linear momentum. So it has, its definition has parallels with the definition of the moment of a force. Any questions? Okay. So now, from the balance of linear momentum for a particle, we can derive another balance law called the balance of angular momentum. So the balance of angular momentum. So this balance of angular momentum, for a particle, we can derive it from the balance of linear momentum, but for a system of particles or for a rigid body, we cannot. For a rigid body, it's a separate balance law, formulated, we call it Euler's second law. But now, for a particle, it's derivable from the balance of linear momentum. Okay, so we'll start with the balance of linear momentum. F is equal to g dot. And guess what we're going to do to obtain moments and angular momentums in this equation? Yes. We're going to cross with what? R. So we're going to do R cross F is equal to R cross g dot. Okay, what is R cross F? MO. That's the moment about O. MO. Now what is R cross G dot? Well, I have that R cross G is HO, right? HO is equal to R cross G. What is H dot O? How do I calculate the derivative of a cross product? I use the product rule. So if I have A cross B dot, it's going to be A dot cross B plus A cross B dot. Okay? So then how do I calculate H dot O? What is it going to be? What is it going to be? Yeah, R dot cross G plus R cross G dot. So that's basically V cross MV plus R cross MV dot or G dot. What is V cross MV? What is it? What is it? What is it? V cross MV, what is it? Why is it 0? Right, it's a vector cross of itself, so that's going to be 0. So I'm going to be left with H dot O is R cross G dot. So MO, which is here, H dot O. Okay, so that's the balance of angular momentum for a particle about the fixed origin O. Okay, so this balance law can be expressed in any coordinate system: Cartesians, cylindrical polar, Serif-Renée. Okay, so now that we've introduced the balance of angular momentum, the next question is going to be, in parallel to the balance of linear momentum, when is the angular momentum of a system conserved? When is the angular momentum of a system conserved? About O. So what I want to be conserved is HO. So under what conditions is the angular momentum of a system about point O, or angular momentum of a particle about point O, conserved? Raise your hand if you agree with this. If H dot O is 0, then angular momentum HO is conserved. Do we agree with this? Take a minute, chat with your neighbor, think about it. When is the angular momentum of a system conserved? Okay, so what do we think? When is HO conserved? When HO is conserved, it means that, okay, so this means that HO, so in other words, HO is constant. This is what it means for the angular momentum about O to be conserved. So H dot O is 0. So these are all equivalent equations, equivalent things. But under what condition is H dot O 0? We would need MO to be 0, right? So this happens if MO equals 0. The sum of moments about O is 0. So again, there was a problem with the printer today. I couldn't print these sets, but could you open up set 12? I'll give you a minute to open set 12. Okay. Do we have it open, set 12? Did you do problem 1 in the exercise session yesterday, the discussion section? Okay. So problem 1 has to do with linear momentum, problem 2 also, problem 3 also, 4. Okay, let's look at 5. So at 5, we're looking at space shuttle orbiter orbiting the Earth. So it's this problem. This is the Earth, this is a space shuttle. It's orbiting the Earth. Okay. So for this problem, what are the forces that are acting on the space shuttle? Gravitational pull, which is going to be towards, what is the direction of the gravitational pull? Towards the center of the Earth. If I take this to be the origin, this is my gravitational pull. Any other forces acting on the rocket? No. So if I want to calculate the moment, sum of moments of this rocket about O, what is it going to be? How do I calculate the moment of a force? R cross F. And here F is Fg, right? But what do we know about MO for this problem? What is it? It's 0. Why? Parallel, right. So that's equal to 0 because, okay. So what can you say about the angular momentum of the space shuttle during its motion? Exactly. The angular momentum of the space shuttle is conserved during its motion. What about the next problem? Read it, chat with your neighbor. Any conservations in the next problem? Okay, so for the next problem, take a minute, think, and then I'll ask you do you have any conservations in the next problem? You might have multiple conservations, actually. So what do we think? Any conservations in the next problem? Let us read it. A particle of mass m moves with negligible friction on a horizontal surface and is connected to a light spring fastened at O. The position A of the particle has the velocity VA is 4 meters per second. Determine the velocity VB of the particle as it passes point B. Okay, so what do we think about this problem? Any conservations? Yes?
From the spring, there's conserved because it's parallel to the position.
What is conserved? The angular momentum. Do we agree that the angular momentum of the mass m about O is conserved during the motion? Let us see. So let us actually solve this problem. Okay. So looks like this. Set 12, problem 6. Okay. So this is happening in the horizontal plane. Gravity is acting vertically down at G. I can draw a Cartesian basis. I can draw a polar basis if I want. If I want to draw the free body diagram of the particle during its motion, what are the forces acting on the particle during its motion? The spring force, the weight. What is the direction of the weight force? Into the page. What other forces are acting on the particle? Normal. Okay. Let me put the cylindrical polar coordinate system. This is the position vector of the particle. This is ER, and this is E theta. What is the direction of the spring force? Yeah. Fs along negative E1. N is along EZ, and weight. What do we know about the normal force here? Is it's equal to the weight? Correct. Why? Yeah, there's no acceleration in the vertical direction. So if I write F equals ma and project along EZ, I'll obtain that the normal force is equal to minus the weight. Okay, so the weight and the normal force cancel out. So when I calculate the angular momentum of the particle, or when I calculate the moment of the force acting on the particle about O, MO is equal to what? The moment of all the force acting on the particle about O, that's equal to what? 0. Why? Because it's R crossed all the forces, right? Which is RER crossed with the weight plus the normal plus the spring force. Now we know that this plus this is equal to what? 0. These are 0. And then this is along ER, and the spring force is along ER, right? So what is their cross product going to be? 0. So again, in this problem, HO is conserved. Okay, we will solve for whatever they are asking for in this problem. But I just want to say first that this type of problems where F is parallel to R, we call it a central force problem. Okay, so this here is a central force problem. F is parallel to r, the position vector of the particle at all times. And then that problem 2, set 12, problem 6 is also a central force problem. Again, what is the central force problem? It's the problem where F, the sum of forces acting on the particle, is parallel to r. And for these problems, the angular momentum about O is conserved. Okay? So now that we know that the angular momentum of the particle is conserved during its motion, how do I calculate the velocity Vb of the particle as it passes point B? The speed. They want the speed Vb as the particle as it passes point B. So how do I calculate that? Any ideas? Conservation of angular momentum. So first I have to calculate the angular momentum of the particle at 2 instances. That's going to be equal, right? So the angular momentum of the particle at A is equal to the angular momentum of the particle at B. So that's RB cross MVB is equal to RA cross MVA is equal to RB cross MVB. And I can cancel out M and M. Okay. So actually here, I care about only the speed, Vb, and I'm given distances and angles. So any ideas on how to proceed? It's actually one quick step, but what is it? Well, what is the definition of a cross product? The cross product of A cross B, how do you calculate its magnitude? Magnitude of A, magnitude of B times sine the angle between them, and the direction using the right-hand rule. So actually, yes, here I can calculate, so the cross products are equal, so their magnitudes are equal. So that's the magnitude of RA, magnitude of VA, and then sine the angle between them, absolute value. Call it theta A. So that should be equal to magnitude of RB, speed of B, and sine the angle between them, call it theta B. So what quantities am I given here? Do I already know? Do I know RA? The magnitude of RA? Yeah, it's 350 millimeters or 0.35 meters. VA, also known, 4 meters per second. What is theta A? $54 is the angle. Well, we're going to take absolute value of sine 54, which then it won't matter, but it's actually pi minus 54. Anyways, since we're taking the absolute value, it doesn't matter. Okay, RB is also given 0.23. VB is what we want to calculate. And that angle is also given sine 65 degrees. So we can now calculate the speed of the particle at point P. Does that make sense? Any questions? Any other conservations in this problem? Yes. Energy. Why is the energy of the particle conserved during its motion?
There's no non-conservative forces.
Well, there's the normal force. That's a non-conservative force acting on the particle. Yes.
Non-conservative forces are worthless.
Exactly. Why is the normal force worthless? Yes, it's perpendicular to the displacement. Was there a question? Yes.
I guess my question is, how do we account, or do we account for the actual mass spinning? Because I don't really know how to phrase this, but so far we've talked about the mass rotating relative to an origin.
Mm-hmm.
But that's just talking about the linear velocity relative to the point.
Mm-hmm.
What about if the object actually has an axis it's spinning around?
Yes, that's a great question. So for a particle, remember we're neglecting the rotation of a particle. So a particle with point mass, there's no rotation. It's a very small, yeah. When we talk about rigid bodies, we'll talk about this again. And we're going to review angular momentum for rigid body, which is much more, it's a different thing. Okay? But it starts from here, yes.
So if the angular momentum of the system is conserved,
Mhm.
like any angular momentum either at v or equal to zero,
Well, here, what is the system?
system is
The particle, right? So during the motion of the particle, its angular momentum is conserved. In particular, at time ta and at time tb, the angular momentum of the particle is going to be the same. So A and B are not two different systems, two different particles. It's the same system at two different times, Ta and Tb. Yeah. Any other questions? Questions? Yes?
Is linear momentum conserved?
Good question. Is linear momentum for this particle conserved during its motion? No, why not? What would we need to have for linear momentum to be conserved? What is it?
Just the spring force?
What about it? The spring force?
The spring force stops it from being?
Well, yes, it is. Because if, yes.
The work in the system is overall just like
Well, for linear momentum, it's not related to work, right? Energy is related to work. Linear momentum is just related to what? What is linear momentum? It's G. G is constant. Well, F is equal to G dot. So G is constant if F is 0, if the sum of forces is 0. Is the sum of forces equal to 0 here? No. Okay. So this is conservation of angular momentum in general. Just for the sake of completion, angular momentum could be conserved in a certain direction only and not totally conserved. So let's write it down here. Angular momentum is conserved along C. This means that HO dot C is constant. So the derivative of this is 0. So H dot O dot C plus HO dot C dot is equal to 0. If this is the case, then HO is conserved along a certain direction C. An example of this is the last problem 8 in this set. For this problem, for example, the angular momentum of the particle as it goes down the funnel is going to be conserved only in the EZ direction. So if you calculate the moment of the forces about EZ, this is equal to MO. So for EZ, that would be a fixed direction. So what would be EZ dot? 0, right? So for EZ, if MO dot EZ, if the sum of moments doesn't have any component along EZ, then the angular momentum along EZ is going to be conserved. When you solve problem 8 at 12, you're going to discover that that's the case there. Deal? Any questions? Yes, you could. I cannot think of a problem off the top of my head where C would be changing and angular momentum would be conserved. It's more difficult to think about. Yeah, or the polar basis, for example. You can think of a pendulum, a simple pendulum. Is the angular momentum conserved along ER or E theta? Maybe, maybe not. You're going to have to do this. Okay. Any other questions? Okay. So we're going to start a new topic, which is collisions. So let me erase the board. So collisions. We're gonna look at the simplest possible collision problem. So we're gonna think of like two cars colliding on the road, and we're gonna try to model this collision, but we're gonna make a lot of assumptions to make us able to model this collision of two cars. Okay, so what happens when two cars collide? Has anyone ever been in an accident? Raise your hand. Okay, not a lot. You drive safe, guys. I got a warning ticket, got in the mail yesterday. Apparently there are new traffic cameras in Oakland. Yeah, but it was just a warning, so next time I have to be careful. Anyways, back to but speeding. Okay, so what happens when two cars collide? The front crumbles, yes. So there's deformation, right? What else? Yes.
Huge
Transfer of energy from where to where?
Normally from large to small.
Okay, so like between the two cars?
Yeah, or person to car.
Yes. Maybe even the deformation. Some energy, right? So there's kinetic energy. The two cars are going at a certain speed. They're going to bump into each other. Kinetic energy is always positive, right? So the energy is going to go somewhere because they're going to come to rest eventually. So maybe to deformation. What else could happen when two cars collide? They can both stop. They can change direction of motion. They can start rotating. Yeah, that's true. Yes.
Occasionally cars fly.
They could fly. Okay. Yes. So collisions is a difficult problem. What we're going to try to do is we're going to try to think of collisions as two particles that are colliding. Okay? So collisions. Okay. We're going to go to a simplified problem. By making assumptions. So I'm going to write our list of assumptions here. Okay, so we're going to consider two particles, and they're going to go through 4 stages. Pre-collision, deformation, restitution, and post-collision. Okay, so it's two particles. So we're gonna call the two particles A and B. No, 1 and 2. Okay. And 1. Okay. So I have the two particles colliding. First assumption from the get-go, since we're considering the cars to be particles, the first assumption we're making is that if we're going from a rigid body to a particle, what is the assumption we're making? There's no rotation. Okay, very well. Then we want to draw the free body diagram of each particle during all of these stages. So if I want to look at the FBDs. So again, I'm going to draw the two particles. Okay. So I want to draw the free body diagrams of the particles in all these stages. So what I'm going to say is that during the motion of the car, before collision, after collision, I have, for example, the weight force, the normal force, smooth forces acting on the car before it collides and after it collides, and even during collision, you have the weight, the normal, and so on. So I'm going to lump all these forces into R1 and R2. So R1 and R2 are all the smooth forces acting on the particle. Okay. So R1 and R2 are the smooth force acting on the particles, and they're going to always be applied. Okay. Any questions so far? There should be a question about what is the difference between the deformation and the restitution stage. So, yes, what are the differences between these stages? What is the difference between pre-collision and deformation? So when does deformation start? Yes, when you start having contact. So the two particles are going to come in contact. When they first touch, then I'm in the deformation stage. What's going to happen in the deformation stage? They're going to deform. Okay. Then I'm going to have a point of maximum deformation. Then I'm going to have some restitution, and then they're going to detach. Okay? So here, I can call this time T0, and here this time T1, and here this time T2. T0 is when the particles first touch. T1 is when I have the maximum deformation of the particles. And T2 is when I have that the particles detach. Now, there are some cases where the particles are never going to detach. There's not going to be any restitution. The particles collide and then just stick to each other and remain this way. So that's possible. It could be that T1 and T2 are the same. There is no restitution. That's possible. You can think of me taking a wad of clay and throwing it on the board. It's going to stick to the board. It's not going to come detached from the board, for example. Okay? So in this case, there is no restitution. Okay. So, any questions? Questions? Yes? Correct. I can put it in an assumption. No change in mass of the particles. Okay, any other questions? Yes. Oh, are all the smooth forces acting on the particle. So I'm combining the weight, the normal, like any smooth force, friction acting on the particle. When I say it's smooth, it means that it's not a delta function. It doesn't suddenly jump to infinity. It's a smooth function. Okay? Any other questions? Okay then. Since we're talking about forces, we were drawing the FPDs, then I can say that pre-collision and post-collision, these are the only two forces acting on the particles, R1 and R2. But then what about during deformation and restitution? What are the forces acting on the particle? What is it? Yes. What is it? Reverberation, okay. Yes.
Like normal contact force.
Yes. Yeah, we're going to call it a deformation force, okay? Well, deformation here, restitution here. So, okay, what's happening? There's a deformation force that's going to act to deform particle 1. So, F1 deformation, F2 deformation. Now, what can we say about these two forces? The force that 2 is applying on 1, the force that 1 is applying on 2 during deformation. They are equal and opposite. So Newton's third law applies. And I'm going to put the same restitution forces. Okay, restitution and deformation forces. What I'm going to do is I'm going to make an additional assumption about the direction of these forces. So when I look at the collision of the two particles, I can draw a common normal between the two particles and a common tangent. Call this T, call this N. A common tangent, a common normal. So for two circles, the common normal is going to be the line joining their centers, right? Common tangent, common normal. Okay? Another assumption I'm going to make, it's going to be that all the deformation and restitution forces are going to be along the normal. So the impact, in other words, the impact is frictionless. So there are no deformation or restitution forces along T. They're all going to be along N. So that's an assumption I'm going to make too. Frictionless. All the deformation and the restitution forces are along N. Okay, does that make sense? Any questions? So there are no forces along T, the tangent to the impact. Okay. What I want to do next is I want to write the linear impulse, linear momentum equation for each particle during deformation and restitution. Okay, before we do that, anyways, no, not before. Okay, so let's do that. I will look at particle 1, M1 during the formation. How does the linear impulse linear momentum equation for a particle look for? Linear impulse linear momentum equation of a particle, how does that look like? Integral of f dt. So the integral, the time goes from t0 to t1. Okay, what are the forces acting on the particle M1 during this time? That's going to be R1 plus F1 d dt. And that's going to be equal to what?
G at time 1.
Right, which is going to be M1. It's the same for the particle. The velocity of the particle not post collision, at time t1, v1 at t1 minus v1 at t0. Okay? That's the linear impulse linear momentum equation for the particle 1 between t0 and t1, right? Does that make sense? Any questions? So let's do the same for all the particles between t1, t0, t1, and then t1, t2. So you do it, I'll do it. Don't look at Weiberg. So M2 during the formation. T0 to T1. Okay, I'll let you finish the other two. Take a minute. So write the two remaining equations. Very good. Underline the vectors. Help your neighbors if they need it. Any questions? Try to do the third one. If you can do it, then you're good. Okay? Oh, you're cheating. You're looking at the book. Very good. Yes. Okay. So yeah, That's the integral now between T1 and T2 of R1 plus F1 restitution dt M1 V1 at T2 minus V1 at T1 and integral okay, right? Yes.
Should it be a V1 prime and V2 prime for the restitution?
Yes. So actually, yes. If you call V2 at T2 and V1 at T2, you can call them V1 prime and V2 prime. Yeah. That's what we will usually do. Okay. Any questions? Can we do this on our own? Adding the impulse and momentum equation from a free body diagram? Yeah? Okay. So the next assumption I'm going to make is that T0, the deformation and the restitution intervals are very small. So, let me, camera. Okay. So T1 minus T0 is approximately, is very less than 1, and T2 minus T0 is much less than 1 also. So the restitution and the collision intervals are very small. So why do I make this assumption? Because if I'm integrating a smooth function, R1, R2, R1, R2 over a very small time interval, what is the integral going to be? 0, right? Remember, what is an integral? An integral is finding the area between the curve and the area under the curve. So if the time interval is very small, then this area is going to get close to 0 if the function is smooth. If the function goes to infinity, then no matter how small my interval is, if it's catching the function when it's peaking, then the integral is not going to be 0, right? So here, since R1, R2 are smooth and the interval of impact and restitution are almost 0, so this I can get rid of, because this integral term is going to be approximately equal to 0. Okay? Another thing I'm going to do is that since all the forces, all these forces are along n, the normal direction n, I'm going to project these equations along n. So I'm going to project along n, along n, along n, along n. I'm going to project, and here I'm going to remove the underlines, because what I'm going to say is that f1d vector is f1dn. f2d vector is equal to f2dn. f1r vector is f1rn. f2r vector is f2rn. Okay? So I'm looking at the linear impulse, linear momentum equations along n. Yes?
I'm a little confused why only the smooth forces become 0. Like, if the time interval is 0, wouldn't that whole integral just basically be 0?
That's a great question. So the smooth forces, yes, go to 0, but the impact forces, these are going to be infinitely large during the interval of impact. So when I'm integrating a function, if I'm integrating a smooth function, low magnitude over a small interval, it's going to go to 0. But if I'm adding something like it's going to infinity in the vertical direction, so the integral is not going to be 0. Yeah, that's a good question. Okay. Any other questions? Okay, so the linear impulse linear momentum equations is like this. Okay, I'm going to make more assumptions. So imagine how complicated this problem is. We're going to need to keep making assumptions so that we can make it into a manageable problem that we can solve by hand. Okay. The other assumption I'm going to make is that at T1, at maximum deformation, the velocities of the two particles along n is going to be equal. So at T1, V1 at T1 dot n is equal to V2 at T1 dot n. So the particles touch, right? They could be moving along T relative to each other. They touch. Along n, they're still going closer together towards each other. At T1, at the point of maximum deformation, their velocities along n are going to be equal. And then they're going to start moving relative to each other again. So at the point of maximum deformation, they're no longer penetrating or separating. They're not penetrating or separating. They're just, the relative velocity along the normal is going to be 0. They can both move together along the normal, but they're not moving relative to each other along n. So that's this assumption. Does that make sense? Kind of? Make sure your neighbor gets it a little bit, understands it. Any questions? I wish I brought stress balls with me today. Does anyone have any? Okay, no worries. So, yes, I'm making this assumption. I'm calling this V2. So that's here. And the dot n becomes 4 here. Okay. Okay, any questions? Okay. The next issue we need to take care of is that the particles are going to deform. The particles are going to deform. How are we going to take into account this deformation when we're talking about particles? The way we're going to do that is we're going to introduce a coefficient of restitution E. So, coefficient of restitution E, which is by definition going to be the ratio of the restitution impulse over the deformation impulse for a particle. So that's equal to the impulse of the restitution T1 to T2 of particle 1 dt along n, T0 to T1 of F1d dt. Okay, and because of Newton's third law, F1r is minus F2r, F1d is minus F2d, so for the second particle it's the same thing. So that's the ratio Okay. I'll let you copy it and then let's think of an interpretation of this ratio. Okay, if there is no restitution at all, what is the value of E? 0, right? There's no restitution at all. Restitutive impulse is 0. So no restitution. E is equal to 0. What if I have full restitution? What is E is equal to? 1, right? All the impulse due to the collision was brought back in restitution, full restitution. E is equal to 1. So our range for the values of E is going to be from 0 to 1. Okay? So what does E encode? It encodes the information about the deformation. So what we can do is we can observe a problem, we can observe pre-impact and post-impact velocities and calculate E, or given E, we can obtain the pre-impact or post-impact velocities given one pair of them. Okay? So E is a number that encodes the magnitude of the deformation, the restitution, the permanent deformation. So if E is equal to 0, all the deformation is permanent. If E equals to 1, it's not permanent at all. So that's why when E is equal to 0, we call that the plastic case versus the elastic case. Okay? Have you taken science of materials? You know about elastic materials versus plastic materials. What's the difference between the two? Okay, time is up. Let's continue. Okay, so okay, general plane impact problem. We have two particles colliding in the plane. Sorry. Given the pre-impact velocities of the two particles, how do I calculate the post-impact velocities? Okay, so I have two particles colliding in the plane. Pre-impact velocities are v1 and v2. I want to calculate the post-impact velocities of the two particles, v1 prime and v2 prime. What do I do? Ideas, think with your neighbor, what do I do? And you're going to use conservations of linear momentum in particular, but you're going to need to know which system and which time. So go ahead, think, and then let me know. Okay, so what do we think? What are some ways we can start to solve for the post-impact velocities? Yes?
You could do a conservation of linear momentum for like pre-collision and post-collision.
For which system?
For the like entire system.
For the entire system in any direction?
I guess in the yeah, any direction.
So let us think. Conservation of linear momentum. Okay. Conservation of linear momentum of the combined system of M1 and M2 during collision in any direction. Is this true? Do we have this conservation of linear momentum for the combined system of M1 and M2 during collision? Yes. Why? No. Why? What do we think? Yes.
We defined it as elastic before, right?
We define what?
Hadn't we defined it as elastic and frictionless?
Well, no, it's not elastic. The collision is not elastic. There is some coefficient of restitution between 0 and 1. Right? Yes. What's in the end direction? The impact forces are in the normal direction. That's correct. So then, do we have a conservation for the linear momentum of the? Under what condition is the conservation of a system conserved? Sum of forces is equal to 0, right? Now, if I consider the two particles here, what are the forces acting on them? Kind of like there, right? These are the forces acting on the two particles. Now, if I consider the combined system of the two, what happens to the deformation and restitution forces? They cancel out, right? Because of Newton's third law, they're equal and opposite. So during deformation, during restitution, the impact forces are going to cancel out. And we made the assumption that the impulse of the smooth forces is also going to be 0. Now, in this problem in particular, the normal and the weight force are in the perpendicular to the page, kind of along the vertical direction, and there's no acceleration in the vertical direction, so they sum to 0. So we don't even need to make the assumption that they're smooth, so they cancel out. However, even if we don't make that assumption, even if we do make the assumption here, the impact forces, restitution forces, they cancel out for the combined system because of Newton's third law. All the smooth forces, their impulse is almost 0. So it is true that for the combined system,